on to Module 4, and then we'll definitely talk about the papers at the end. All of Module 6 was the paper. So this is really the last contextual model with content in it. Okay. Any questions from that module? No, okay. All right, so there are, for me, key principles in epi and stats that are the must-knows. If you don't know these topics or understand these topics, please seek out either training or resources or online classes or textbooks, whatever it may be, online texts, to make sure you understand these principles. I'm going to go over them in a very overarching manner. I'm not going to get into them in a granular way, so it may not be sufficient depending on the level of knowledge you've come here today with. And I can't assume that's the same, so I'm hoping I'm not going through it too fast or too slow for this audience. In epi, we have something we call the population. And this population begins with different layers of people. The biggest layer, the widest, broadest layer is what I like to call the target. And that's the group to whom I hope to refer all of my findings. They apply to that whole group. There's several other layers, but before I get into them, I just want to let you know, walk you through the epi principles we're going to discuss are the populations, the study designs, the meaning of validity, sources of bias. These are very simple concepts. They're critically important. Every time you read a peer review paper, these things should be on your mind as you read the methods and as you interpret the findings after reading the methods. And then finally, for the stats principles, we're going to go over what an effect estimate is, how to interpret a confidence interval and a p-value, and a reminder of what are your sources of error and how to achieve optimal power. So I was talking about the target population. Again, this is the broadest group to whom you hope to say something about. Rarely are we in a situation where we ever get to generalize to the whole US population. In my work, I'm already limited to men. Nothing I have to say in my work will ever relate to women because they don't have a prostate gland. So the work itself will be maximally applicable to men in the US. But even from there, I have to often back up a step because even with my large cohort, which is racially diverse, we have an underrepresentation of Hispanic men and Asian men in our cohort. That's changing as the face of the military changes and as men age who came into the military in their 20s who were Hispanic and Asian. There's a huge rise in that, but they're not in an age yet where they're getting prostate cancer. So they haven't found their way into my database yet. They will in 20 years. But for now, I can't even say that my results are generalizable to all males in the US because I'm missing two core ethnic racial groups that we just don't have. And I can't be faulted for it. They're not the face of the military yet at this age group. The actual population is then drilled down into those who meet the conditions of your study. I mentioned earlier being very clear about the inclusion-exclusion criteria, and in your flow diagram that you create, whether it's for yourself or for the paper, main figures or supplementary figures, whatever you choose, that figure will help you understand who your actual population is. Because after you've started with the greatest group you have and you walk through all the reasons people fell out of the analysis, you're left with the actual population up to a point. The final population is the one in your study, and that is what we call the study population intuitively. Those are the ones who actually have the data. If I'm missing a patient because his age at diagnosis is missing, but he's eligible in every other way, because age wasn't a restriction criteria in my study, but at the end of the day, as I get to the final population, he is missing his age. In the multivariable model I conduct, he's going to fall out because age is going to be a variable I model. So that becomes my study population. And it is important to talk about the potential differences between those three groups. In an ideal world, you'd be able to create a table that compares them and says, hey, look, my study and my actual are almost the same. Missing data don't skew my population in any meaningful way, but that's often hard to do. We don't always have enough information to say that for sure. And so we have to be thinking about the biases that we may be introducing into our study as a result of missing data. That's always very important, and everyone is dealing with missing data always. I can't think of one study I've ever seen where there were no missing data. Designs. I mentioned earlier that there's a rigor, a ladder of rigor is how I like to think of it, from the least to the most. And at the place where you see the greatest rigor, the bottom of the slide, the RCT, or just clinical trial if it's not randomized, but the real gold standard is the randomized double-blind placebo-controlled trial. We're not always able to conduct that, not only because it's expensive, but as I mentioned earlier, the question you're asking may not lend itself to that. It may not be appropriate. In fact, for my written qualifying exam in grad school, we had to choose one of 5 questions to write a grant on. And the grant had to be airtight. You had to think of every problem. And it was super stressful. And you got one chance to be reviewed. And if your advisors didn't like it, you got one more chance. And then you get kicked out of the program if they didn't like it still. So nobody wanted to fail the first round, ever. Because then you'd just be under so much stress. I can't imagine life. And so you come at this question and you want to poke every hole in it. Well, the question I got was, does residential radon increase the risk of lung cancer? And the problem with it is we're a highly mobile society. How do I measure radon? How can I possibly know your residential radon history and where all the places you've lived if you kept moving around your whole life? I won't know. The summation of all your exposure will be very difficult, if not impossible, to measure. So I tried to think through, well, what kind of unique characteristics would a population need for me to be able to accurately measure the key predictor in my study, residential radon? How am I going to measure that well? So I came up with the concept to pick counties in the US that had variation, because you want some variation, of very low levels and very high levels. So there was heterogeneity in the exposure metric, low, medium, high, and places where people never moved. Places where I could go into your home and you're in the same house your whole life, or you move down the street and you're in the same. One of the best places, Lancaster County, Pennsylvania, the Amish community. And, oh, beautiful. It's a beautiful country. And it became the selling point of my grant. I mean, when the environmental epidemiologist reviewed it, he didn't know who had written it, and I wasn't supposed to know what he said, but he kept going on and on about, like, oh my gosh, we need to do a study now in the Amish country. And you know what? I'm not that smart. Like, I'm not giving myself more credit than I deserve. But what I paid attention to was, right, what are the characteristics that are going to make this question, make you answer it the right way? You need to understand the holes. The holes for me were the variability in this measurement, how hard it was going to be to measure that accurately. So as you think about the design, my study was a case control design, but look where that is on the rigor of this ladder, not that high. And yet it was loved, because even though a prospective study would have been far more rigorous, you'd have to follow men for 50 years, living in some house that you knew about at a young age, and then know what happened to them 50 years later to have enough people that developed lung cancer to have an adequate sized endpoint. So you have to be thinking about what makes sense, not just what's the most rigorous. So even though this is a hierarchy, sometimes you do belong here. Sometimes it's okay to be in the middle. It's not always a bad thing. And so don't let a reviewer knock you down too hard. That's one of the points I wanted to make, for the fact that your data may be observational. It may be absolutely appropriate that you're using observational data. So that may not be necessarily an awful limitation that you have to keep apologizing for. Okay, validity. So there's really 2 key buckets of validity, internal, external. External is really kind of out of your control unless you're able to pick a population to study that is going to represent everybody in the US. We often can't do that. But it's important to be aware of and to maybe say in your limitations what the limits are to the generalizability, external generalizability. I often see it just left as the term generalizability without clarification. Is it internal or external? The internal has to do with being able to repeat or reproduce the same findings. This is especially problematic in the dietary literature, where the same question can get asked 15 times and there's 16 different solutions or answers, because it's hard to measure diet well. And it's usually not the case that a single micronutrient in your diet explains all things. Our diets are complex. We engage in patterns of behavior. If you're eating well, you might also be working out, and you may not be a smoker, and you might be drinking less. So patterns and clusters of behaviors all need to be accounted for. We can't do that very well. It's very hard to do dietary epi. I bow to the people that do it well, because I just feel sorry for them. It's awful. I would never have picked that field. So that's one important thing, though, is can we reproduce our findings? If we can't, how much weight am I going to put on them? And reliability or accuracy, I'm going to show you a diagram, because this is often better shown in a picture than in words. If I were able to hit this target very accurately in the center, but my data points are all clustered. What have I maximized? I'm very unbiased, but it's precise. So there's a narrow range. This is kind of, you'd think this is always where you want to be. But if I'm comparing, let's say, in my residential radon example, if everyone has the exact same level, let's say I had only focused on Lancaster County, and everyone had the same level of radon, and there's no variability. Everybody's between 4 and 5 picocuries per liter of air in their homes. How am I going to show that it predicts anything? Everyone's the same. It's like if you all ate oranges and I was trying to prove that oranges cure lung cancer, how would I show that there's any differences if I can't compare the orange eaters to the non-orange eaters? I need variability in my predictor. So if I'm using a predictor that's very accurate but has no variability, I'm going to have a really hard time showing a difference between the levels of those who have exposure, don't have exposure, eat the orange, don't eat the orange, and some outcome of interest to me. The letter B is unbiased, but not precise. So this is not accurate. Why is that? Because I'm not getting at the place I want to get at. I'm not targeting the metric I want. It's dispersed everywhere. Letter C, and the only letter that's accurate here is obviously A, but letter C, I just want to walk through each of these, it's precise, right? Everybody's clustered in one little area. That's great. But guess what? It's not at the target. You're way off center, but you're being very consistent. It would be like taking someone to a gun range that was super good at shooting a specific spot, but was never hitting the target. Terrible example, I'm sorry. The final plot, you're biased and you're not precise. Not only are you not hitting the target, but your spots are everywhere. So these are just issues in understanding validity that I think we all need to be aware of, that we sometimes don't do things in a precise manner and they're not accurate, but they're different concepts. Confounding, oh gosh. So confounding is a nightmare. It is something that is surely in almost every study we do, especially in epi. We worry about it. There are things that we know matter that we're not measuring. But the reason we see confounding is a special reason. The confounding factor will create a spurious association. You will falsely believe that you have found something, or you have shown a negation effect of something reduces the impact of an outcome, or it escalates the odds of an outcome. That factor has to be associated with your key predictor, and it has to be independently associated with your outcome. It has to be both things. And typically, it is not on the causal pathway. Sometimes it is. Almost 99% of the time it's not. But it has to be independently associated. If there's not an independent association, it can't be a confounder. The way we detect it is we stratify our data across that factor. So I like to think of this simple example. It's kind of oversimplified, but 20 years ago when the earliest studies were trying to show an association between alcohol consumption and lung cancer risk, we all know that smoking was the most important factor of all when you're talking about lung cancer risk. So how do we address it? Well, some studies didn't. And guess what? What do we do more? What do people who drink potentially do more? Smoke. Right. So if you're a drinker who's also smoking more, those behaviors are independently associated, apart from your outcome of lung cancer. It has nothing to do with lung cancer because you haven't gotten it yet. But if you're a drinker, you might also be a smoker, and vice versa. So those two behaviors are highly correlated. So the way to deal with this, per the last bullet, would be to divide the cohort and the data into two separate groups, the non-smokers and the smokers. And even in that crude group of smokers, I might not even need to say how much you smoke. I might not even need to know that you are a heavy smoker or a light smoker, a daily smoker versus a weekly smoker. I'm just going to put that if you smoke anything, you're in one contingency table. And if you don't smoke at all, and I better measure that right, then you're in another. The association between alcohol use and lung cancer risk went away because all of that effect was driven by the fact that they hadn't adequately handled the issue of smoking. And we do this because we don't always know. Like, this is such a simple example because we have all the answers now. We know all these relationships, but what if you didn't? What if you weren't sure about a factor that was in the environment that someone was exposed to that was causing your outcome, and you're studying a predictor that is independently associated with that exposure and that factor, you could falsely find an association. And we see this in the dietary literature all the time because of how behaviors cluster. So this is a very crude breakdown of how you would stratify data. On the left, you see the data collapsed. This is a contingency table that does not consider smoking status. It only shows the relationship between alcohol consumption and this is so simple, forgive me. It's just simple dichotomy. I wanted to keep the example simple between yes, you drank alcohol, no, you did not. So it's a yes or no. And then did you get lung cancer, did you not? Super, super crude and simple. It's not how you would probably want to model something. On the right, you see true smokers at the top, and you see non-smokers at the bottom. Now, if I fail to account for smoking, guess what? I'm going to report in my paper that there's a more than twofold increased odds of developing lung cancer if you drink versus you do not drink. That's the single sentence I would take away from that table. When stratifying on smoking status, I now see that there's no association between alcohol and lung cancer for either smokers or non-smokers. The effect goes away. Now, I don't have p-values and confidence intervals here, so you have to trust me, the p-values aren't significant. But the point is that stratifying your data is a great way to handle a potential confounder. It's actually the most important way. The only time we can't do it is when we don't have enough patients. So imagine that all of these cells over here were 10s and not in the 20s and 30s. And now I break you out into smokers, non-smokers. I see a 2-cell and a 2-cell here. Now I'm going to see a whole bunch of little cells because I've only got 10 and 10, 20 total to break out into 2 groups. So when you're dealing with very small sample sizes, stratification may not be a solution, but most often we're in a situation where we can stratify, and we should. Effect modification is a very different concept. It's often confused with confounding. Effect modification is the appearance of multiplicative effects when combining 2 factors in predicting an outcome. So instead of you adding the effects and the impact of each independently, it almost looks like the effect is multiplied. I'll show you an example in a moment. Another great example, also in the smoking literature, I apologize, it provides the best examples because the odds ratios are always so dramatic. If you're looking at cigarette smoking and a history of asbestos exposure, but you're trying to study lung cancer, you want to understand what might be the joint impact of being both exposed to asbestos and being a smoker. So this relationship, when you look at one factor alone, if you ignore asbestos and you only look at smoking and lung cancer, the relative risk of developing lung cancer is 20. I mean, we don't see odds ratios like that very often, but for smoking, that's actually accurate, sadly. For with asbestos, oh my gosh, it goes up to 64. So it more than tripled the relative risk of developing lung cancer when you looked at both factors in combination, smoking and exposed to asbestos. One of the telltale signs that you've got a situation of interaction, and just FYI, the term effect modification is the more appropriate term, but you will sometimes hear it interchangeably used with interaction. But what you need to really be careful about is what that means is statistical interaction, because there's also a very real biological phenomenon known as biological interaction, which is not the same. I'm rushing through this, I apologize. These are just the key principles that I want you guys to hear today. So one of the key telltale signs in interaction is that if you were to plot the lines between risk and categories of exposure, the lines would cross. If they're parallel, the way they are on the left side of the screen, there's no interaction. If they ever cross, and here they cross very significantly, you're dealing with interaction. So plotting your data is another way to help you reveal, but I think just looking at the relative risk going from 20 to 64 is sufficient for me. I don't even need to plot my data at that point. So I keep using these terms, relative risk, odds ratios. What am I talking about? In every analysis from any statistical model, you want to produce an effect estimate. The rate of a disease in one group over the rate of the disease in another, and compare them. If the value is above 1, that means that that factor increased the risk of some outcome. If the value is below 1, then it decreased the risk of some factor. And we'll talk about confidence intervals in a moment. I don't have time to get into how we compute all of these, but it's very important to understand that an odds ratio comes from a retrospective study where you weren't in control of time. You started with a data set and you went back and looked at what happened in the past. Most of the analysis I do with my cohort is retrospective. We have a couple of sub-studies nested within that are prospective. Prospective work takes decades to complete. Only NCI that funds the huge, $100 million trials can really conduct good epi in a prospective manner. Most of us can't. So you're either dealing with case control cohorts where you're retrospectively going back and assigning status as exposed, not exposed, diseased, not diseased, or you're doing it retrospectively, but you're coming up with an odds. So this is the probability estimate. When we're talking about risk, you've got real-time data. You've got a real rate that you're modeling, and you're understanding the impact of time. And very often the difference you'll see is that person time is in the denominator instead of just number of people. It'll be people times the amount of time they contribute, summed up in the denominator. And I see faces glazing over, so I'm going to try to be less statistical, I promise. But it's important just to appreciate that a relative risk comes from the more rigorous designs, but you don't always get to have it because not all of us can be doing prospective research, and that's okay. But when you're dealing with odds, it's from designs that are a little lower down on the ladder rung of the hierarchy of study designs. Confidence intervals are probably one of the most poorly understood concepts, and I hear people misquoting what they mean all the time. And I'm going to say it basically as a factor of noise. A confidence interval shows you, here's your effect estimate in the middle, you've now calculated it, but how noisy is it? How precise was it? Did you have 5 men in your study and the confidence intervals range from 1.1 to 100, which is terrible? I don't know where to have faith. Where in that interval is the true estimate? The definition of a confidence interval is if you had the ability to repeat your study over and over and over, 95% of the time, your actual true odds ratio or relative risk would be that number. That it would be in that interval and it would be that number if you could just repeat the study over and over, which we know we can't. And we set the value at 95%. We arbitrarily choose that and accept it. And that's the value you will see in almost all the literature. Occasionally I see 99%, but most often I always see 95%. We are allowing for error. We know we are. And what does that mean? What do you mean I'm allowing for error? When we calculate a p-value, the p-value is the probability that I would find that number again and again and again. So if your odds ratio, if you remember for the smoking asbestos group, is 64 with a relative risk, if I were to look at that study, what is the probability that that estimate is not right? I have arbitrarily set that at less than 5%. And that's just a standard in the field. And again, because we know we don't measure everything correctly. We know there's a chance that you're getting the wrong answer. And I think that makes people very uncomfortable in the sciences. And that's why these numbers are set so low. Under 5% is considered acceptably low. So what are these types of error I keep talking about? Well, there's really 2 critical types of error. There's type 1 and there's type 2. Type 1 is also known as alpha error, and it's what we use to set the p-value. We know that there's going to be a certain amount of time that we reject a true null hypothesis, that we say wrongly the null hypothesis is wrong. And we don't want to say that if we're wrong, right? We want to have a low probability of saying that. Type 2 error is kind of the opposite. It's when I fail to reject the null, when I'm actually wrong and I fail to reject it and I accept it. So we want that probability to be a little less wide. We're okay with that. We're a little more okay with that than the other option. And we actually define power on the basis of the beta error or type 2 error, where your power in any power calculation is 1 minus that factor. Almost invariably in any grant, in any study, you'll typically see power arbitrarily set at 80%. That's just kind of the common standard. I just want you to be aware of it, where it came from. People have just agreed that that's an acceptable amount of error. And if I had to put in words the definition of power, it indicates the ability to correctly reject the null of no association when a significant one exists. So why am I more comfortable with rejecting that why would I be more comfortable with that problem than the other problem? Does anyone have a thought about why is it okay to have a larger beta error than an alpha error? It's a little arbitrary, but basically I'm more afraid of being wrong about something that could be helpful than being wrong about something that won't be helpful. So I'd rather give myself more freedom to reject something that I wish to show was true and say, oh, darn it, I don't have a significant finding, than to be wrong and tell to the world, oh my gosh, I found something really exciting and new, and you should all adopt my new finding into your practice because this predictor actually will reduce the odds of some bad disease. If I'm wrong about that, I don't want that probability to be very big because now I'm sharing the news with the world that I found something exciting and I'm sharing it and I'm wrong. I want that error to be very, very small. I'd rather say to the world, I didn't find anything, sorry, it doesn't change the field stays the same. I'm so sorry, this finding's just not interesting. I'm better off making that mistake than the mistake of telling everybody to change everything they're doing because I found something new. Does that make sense?